Hello everyone, welcome to the video lecture of this course finite element method. So this is the fifth module that we are discussing here. So in the earlier lectures regarding this fifth module, we have discussed the concept of the isoparametric element, then superparametric and subparametric elements. Then we have seen the different formula of the quadrilateral element, when how the shape functions are varying, and then the formula for the strain displacement matrix, then the stress strain relationship matrix, then the formula for the local coordinates or the natural coordinates, and the local or the Cartesian coordinate, and the Jacobian matrix. So for all these different terminology we have seen their different formula, and based on all those formula we have discussed several numericals. So in this lecture also we will discuss one more complicated numerical regarding these isoparametric elements, and after that we will discuss one new topic, that is serendipity elements, and then we will discuss how the shape function formula is varying for this serendipity element, and regarding that what is the Gaussian quadrature. So these topics will be discussed in this lecture. So let us start this lecture. So these are the course objectives and course outcomes. So all these things are known to us already. And this is the COPO mapping for this subject finite element method. So we will start with this problem regarding the determination of the Jacobian matrix, and here we can see that one quadrilateral element is given, and regarding this element we need to determine the Jacobian matrix. So let us first write what are the things given in this numerical, and we can see that for this quadrilateral element the coordinates of its four different nodes are given, that is x1 y1, then x2 y2, then x3 y3, and x4 y4. These four coordinates are given here for this quadrilateral element, and we need to find the Jacobian matrix. So we will proceed with the formula of the shape function for this isoparametric quadrilateral elements, and as we have discussed this formula of the shape function earlier also, so we know the formula. Like for n1 it is 1/4 into 1 minus epsilon into 1 minus eta. Then for n2 it is 1/4 1 plus epsilon into 1 minus eta. It is equation number 2. Then n3 is 1/4 into 1 plus epsilon into 1 plus eta, that is equation number 3. And n4 it is 1/4 into 1 minus epsilon into 1 plus eta, that is our equation number 4. So these are the equations for the shape functions for the given isoparametric quadrilateral element. Now for this quadrilateral element the Cartesian coordinates can be represented mathematically as x equals to n1 x1 plus n2 x2 plus n3 x3 plus n4 x4, and y equals to n1 y1 plus n2 y2 plus n3 y3 plus n4 y4. So these are the equation number 5 and 6. Now if we put the value of n1, n2, n3 and n4 and the values of x1, x2, x3 and x4 in equation number 5, then we are getting this equation number 7. Next, similarly, If we put the values of n1, n2, n3, n4 and y1, y2, y3, y4 in the equation number 6, then we are getting the equation number 8 here. Now simplifying the equation number 7, we are getting a relation in between x, eta and epsilon, which is equation number 9. Now if x is this equation number 9, then we can perform this differentiation, that is del x del epsilon, this is equals to 1/4 plus 0 plus 0 plus 8 minus twice eta, which is actually 2 minus 0.5 eta, which is our equation number 10. In the similar manner, if we perform the differentiation with respect to eta, then we can get the equation number 11, where we are getting the del x del eta, this is equals to 1 minus 0.5 epsilon. So in this similar manner, from equation number 8, after simplifying that, we are getting the value of y is 1/4 into 7 plus 11 eta minus epsilon plus 3 epsilon eta. This is our equation number 12. So if y is this one corresponding to this equation number 12, then del y del eta, del y del epsilon, actually this is equals to 0.75 eta minus 0.25, which is equation number 13. And if we perform this differentiation with respect to eta, then we are getting 1/4 to 0 plus 11 minus 0 plus 3 epsilon, that is equation number 14, where we are getting del y del eta, this is equals to 2.75 plus 0.75 epsilon. Now we need to find the Jacobian matrix for this given quadrilateral element. So that means we need to write the formula of the Jacobian matrix, that is J matrix. This is J11, J12, J21, J22, this 2 by 2 matrix. Now here we know that J11, this is del x del epsilon, and J12 it is del y del epsilon, and J21 this is del x del eta, and J22 it is del y del eta. If we put the values of all these parameters or all these elements, then we are getting the final Jacobian matrix like this, which is given here as the result. So this Jacobian matrix, it is in terms of the elements of this Jacobian matrix, it is in terms of eta and epsilon, it is in terms of the natural and local coordinates. So this is the procedure here that we have followed. We have used the formula of the shape functions and the formula of the local coordinates. Then we have put the value of the shape functions in the formula of the local coordinates, and finally we have got one relation in between x then eta epsilon and another relation in between y eta and epsilon. From these two different equations we have performed the differentiation with respect to epsilon and eta, which are the elements of the Jacobian matrix. So this is the procedure which we have followed here to obtain the Jacobian matrix for the given quadrilateral element. Now let us discuss one new topic, that is known as serendipity elements. So what is this actually, the serendipity element? The higher order Lagrange elements, they contains internal nodes which do not contribute to the inter-element connectivity, but this can be eliminated by condensation procedure, which needs extra computation. Now the elimination of these internal nodes results in reduction in size of the element matrices. So on the other hand, it is said that one can develop the shape functions of two-dimensional elements which contain nodes only on the boundaries. So these elements are called the serendipity elements, and their interpolation functions can be derived by inspection in terms of natural coordinate system. So this is the concept of the serendipity element. So in a simple manner we can say that the shape function of two-dimensional element which contains nodes only on the boundaries. So these elements are called serendipity elements. So in this diagram, figure 5.21, we can see the two-dimensional serendipity elements and Pascal triangle it is shown. And for the linear element, then quadratic element and the cubic element, these are given here. Now the relation, it is the interpolation functions in terms of the natural coordinate system for this serendipity element, it is given here. Like number A, in case of the linear element, Ni is a function of eta and epsilon. It is written as 1/4 1 plus epsilon epsilon I multiplied by 1 plus eta eta I. It is equation number 5.66. Then for B quadratic element, we are having three different cases. That is for nodes epsilon equals to plus minus 1 and eta equals to plus minus 1. In that case, we are getting the equation number 5.67. Then for nodes at epsilon equals to plus minus 1 and eta equals to 0, in this case we are getting the equation number 5.68. And for nodes at eta epsilon equals to 0 and eta equals to plus minus 1, in that case we are getting the equation number 5.67. Next, for the cubic element, we are having two different cases, and for nodes at epsilon equals to plus minus 1 and eta equals to plus minus 1, then we are having the equation number 5.70. And for nodes at epsilon equals to plus minus 1 and eta equals to plus minus 1/3, then we are having the equation 5.71. So these are the formula in case of the linear, quadratic and cubic element corresponding to their cases, different cases which are given here. Now there is one derivation of the shape function for 8 noded rectangular element. So we can see in this diagram we have considered a 8 noded rectangular element, which is given here is equation in figure number 5.22. Now it belongs to the serendipity family of elements. It consists of 8 nodes which are located on the boundary. So in this 8 noded quadrilateral element, the figure A, it is represented in XY space and figure B in epsilon eta plane. The two different kinds of representation. Now the shape functions here, n1 equals to minus 1/4 1 minus epsilon into 1 minus eta into 1 plus eta plus epsilon, and 2 is equals to minus 1 by 4 into 1 plus epsilon into 1 minus eta into 1 minus epsilon plus eta. Next, for n3, n4, n5, n6 and n8, we can write this equation for the shape function. So how we have written all these things for the 800 quadrilateral element? So from here, in case of the quadratic element, for the nodes for the three different cases are given, and from this we have written this part. So we have till now we have written the formula of the shape functions for the 8 different nodes of this quadrilateral element. Next, the shape function derivation for the 6 noded triangular element. So in this diagram you can see a 6 noded triangular element is shown. Now it also belongs to the serendipity family of elements, and it consists of 6 nodes which are located on the boundary. So the shape functions can be written in this manner, like n1 equals to l1 into twice l minus 1, then n2 equals to l2 into twice l2 minus 1. So in this manner we can write the shape functions for this 6-noded triangular element. Now let us discuss one numerical based on this concept. So here it is given that we need to consider the 8-noded quadrilateral element defined by the following nodal coordinates. So the values of x1, y1, x2, y2, x3, y3, and in the similar manner up to x8, y8, these are given for the 8 different nodes of this quadrilateral element. Now we need to determine the global coordinates that corresponds eta equals to 1 and epsilon equals to 0.75. So for this 8-noded quadrilateral elements corresponding to its different nodes, the coordinates are given, and we need to determine the global coordinates that corresponds to eta equals to 1 and epsilon equals to 0.75. So first we will write the formula of the coordinate, that is x equals to n1 x1 plus n2 x2 plus n3 x3 plus dot dot up to n8 x8. So this is our equation number 1. And the value of y, this is n1 y1 plus n2 y2 plus n3 y3 plus dot dot up to n8 x8. So these equations are known to us equation number 1 and 2. Now in case of this quadrilateral element, at node 1 the value of n1, this is minus 1 by 4 into 1 minus epsilon into 1 minus eta into 1 plus epsilon plus eta. This equation we have seen earlier, like here. In this case we have seen the formula of the shape function for n1 up to n8. So these 8 formulas we need to remember and apply here in this current numerical. So first the formula of n1 we have seen. Now here in this formula of the shape function 1, we need to put the value of eta equals to 1 and epsilon equals to 0.75, which are given in this numerical. If we put the value of this epsilon and eta here in the formula of the shape function 1, then we are getting the value of n1 equals to 0. So in this similar manner we need to write the formula of n2 corresponding to node 2. This is minus 1/4 to 1 plus epsilon into 1 minus eta to 1 minus epsilon plus eta. Now if we write the value of eta equals to 1 and epsilon equals to 0.75, then finally we are getting the value of n2, this is equals to 0. Next, in case of n3, that is the shape function corresponding to node 3, the formula is minus 1/4 into 1 plus epsilon into 1 plus eta into 1 minus epsilon minus eta. Now here if we put the value of eta equals to 1 and epsilon equals to 0.75, then after several steps we are getting the value of n3 equals to 0.656. Next, at node 4, the formula of the shape function, this is equals to minus 1 by 4 into 1 minus epsilon into 1 plus eta into 1 plus epsilon minus eta. Now here if we put the value of eta equals to 1 and epsilon equals to 0.75, then we can write n4 equals to minus 1/4 into 1 minus 0.75, which is 0.25, then 1 plus eta, which is 1 plus 1, that is 2, and 1 plus epsilon minus eta, that is 1 plus 0.75 minus 1, which is equal actually 0.75. So the value of n4 we are getting here is minus 0.0937. So we need to continue this process to calculate up to n8. So in case of n5, which is the shape function corresponding to node 5, so n5 equals to half 1 minus epsilon square into 1 minus eta. Now the value of epsilon is 0.75 and the value of eta is 1. So that means you're getting half into 1 minus 0.75 square into 1 minus 1, which is 0. So that means the final value of n5, it is coming as 0. Next, corresponding to node 6, the formula of the shape function, it is half into 1 plus epsilon into 1 minus eta square. Now here the value of eta is 1 and the value of epsilon is 0.75. So finally we are getting the value of n6 is 0. Next, at node 7, the value of the formula of the shape function, it is half into 1 minus epsilon square into 1 plus eta. So now if we substitute the value of eta equals to 1 and epsilon equals to 0.75, then we are getting n7 equals to half into 1 minus 0.75 square into 1 plus 1. So if we calculate this part, then finally we are getting n7 equals to 0.437. And finally for node 8, the formula of the shape function, it is half into 1 minus epsilon into 1 minus eta square. So now if we substitute the value of eta equals to 1 and epsilon equals to 0.75, then we are getting the value of the shape function n8. This is equals to half into 1 minus 0.75 into 1 minus 1 square. So finally the value of n8 equals to 0. Now if we put the values of all the 8 shape functions and the values of the x coordinates for the all different 8 different nodes, then finally we are getting the x coordinate of as 1.656. So in this similar manner, if we put the values of all the 8 different shape functions and all the y coordinates corresponding to 8 different nodes, then after several steps we are getting the value of the y coordinate as 1.5937. So that means the final result of the global coordinate, it is x equals to 1.656 and y equals to 1.5937. So this is the final result which we got here. So what we have done, that to calculate the global coordinate, that is x and y, we have first written the values of the shape function for the 8 different nodes. Now there we have entered the value of the epsilon and eta, and finally we have calculated the value of the shape 8 different shape functions. Next we have used the formula of the coordinates x and y. There we have entered the value of the 8 different shape functions and the given coordinates, given x coordinates and y coordinates for the 8 different nodes of this quadrilateral element. And in this way we have calculated the value of x and y, which are the global coordinates for the given quadrilateral element. Next we will discuss the numerical integration, that is Gaussian quadrature and application to plane stress problems. Now this Gaussian or Gauss quadrature, it is one of the numerical integration method to calculate the definite integral, and in finite element analysis this Gauss quadrature method it is mostly preferred. So in this method the numerical integration it is achieved by using the expression which is given here as equation number 5.72. And the equation is integration minus 1 to 1 fx dx. This is equals to summation I equals to 1 to n wi fxi, where wi is the weight function and fxi is values of the function at predetermined sampling points. So this formula, that is equation number 5.7872, actually we need to remember, and based on this formula in the next lecture we will discuss several numericals, how to solve different numericals of this Gaussian quadrature concept. Now the function fxi is calculated at several sampling points, that is n equals to 1 2 3 dot dot, and each value of fxi is multiplied by weight function wi, and finally all the terms are added and it gives the value of integration. So this is the formula and the concept of this Gauss or Gaussian quadrature in case of the finite element analysis. And this formula, that is equation number 5.72, you need to remember, that is integration minus 1 to 1 fx dx. This is equals to summation I equals to 1 to n wi fxi. So this form where wi is the weight function and fxi is values of the function at predetermined sampling points. Next we are having one table related to the Gaussian quadrature. Now it shows the location of Gauss sampling points, that is fxi, and corresponding weight function wi for different number of points. So this table it gives Gauss points for integration from -1 to +1. The formula regarding this Gaussian quadrature, it is -1 to 1 fx dx equals to integration, it equals to summation I equals to 1 to n wi fxi. Now in this table 5.1 we can see that the number of points, that is n, that is given as 1 2 3 and 4. In the location xi, it is if number of point is 1, then x1 this is when 0.0, and the corresponding weight, that is wi, this is equals to 2. Next, when the number of points n is 2, then the location, this is x1 and x2, this is equals to plus minus root under 1/3, that is plus minus 0.577, and its corresponding weight it is 1. Next, when the number of point is 3, then we are having x1 x2 and x3, but x1 and x3 this is equals to plus minus root under 3/5, so which is plus minus 0.77459, and x2 this is equals to 0. Now corresponding to x1 and x3 the value is plus minus 0.774, then corresponding weight is 5/9, which is 0.555, and corresponding to x2 where value is 0, then the corresponding weight it is 8/9, which is 0.888. Now if the number of points are 4, then the value of x1 and x4 this is plus minus 0.8611363116, and its corresponding weight it is 0.3478. Again here we are having 4 different points, so x2 and x3 its values are plus minus 0.3399, and its corresponding weight is 0.652145. So this table it's showing the Gauss sampling points and corresponding weight function for different number of points. We need to remember to solve the different numericals based on this Gaussian quadrature. So these are the different concepts that we have discussed in this lecture. First we have discussed one numerical to calculate the Jacobian matrix. Then we have discussed the concept of the serendipity element, and there we have seen different formula for the linear, quadrilateral and cubic element. And based on the concept of the serendipity element, we have discussed one numerical. Next we have discussed the concept of the Gaussian quadrature and one important table regarding this Gaussian quadrature we have seen, and we need to remember this table regarding the Gaussian quadrature, by the help of which we will discuss different numerical in the next lecture. So in the next lecture we will use this Gaussian quadrature table to solve different numerical problem. This is the end for this current lecture.